Have an exemplar of circular motion past paper question, and I thought I would talk you through it to help you see how this is done if you're having any difficulty. So it says a lead ball of mass 0.25 kilograms. So there's an important fact for us, that 0.25. Is swung round on the end of a string so that the ball moves in a horizontal circle of radius 1.5 meters. The ball travels at a constant speed of 8.6 meters per second. Calculate the angle in degrees through which the string turns in 0.4 seconds. So, I know, as always, I write down the things that I know from the question. Actually, I'll just copy and paste that. It will come through with the highlighting. Okay. So, I want to know the angle. So I'm thinking angular speed. It's not the only way of doing this, but I'm thinking angular speed. So I'm thinking I've got V, I've got R. If I had omega, then, and of course I have the time, which I haven't highlighted, but I have the time as well. And just stick that in there too. We have time equal to 0.40 seconds. And I'm noting I've got two sig figs throughout here. So I'm thinking angular speed, I'm thinking V equals R omega. So I've got V and R. So that then gives me omega equal to V over R. And V is 8.6, R is 1.5. So that gives me omega as 5.73 radians per second. So I know how many radians per second, I know how many seconds. So my angle then is omega times t, which gives me 2.29 radians. But remember, I want it in degrees. So now I have to convert from radians into degrees. And of course, converting radians into degrees, each radian is 360 over 2 pi degrees. So there we have 130 degrees. So 130. Calculate the tension in the string. Well, we're looking at a horizontal circle. So the weight of the ball has got no effect here because that's obviously vertical. So the tension in the string is the only force involved in providing the centripetal force. So tension must equal the centripetal force. So there's my first thought, that my tension will equal mr omega squared or mv squared over r. I might be tempted, given that I know v, to use v as well, but I've worked out omega and I'm happy with that. So v squared over r, mv squared over r, or mr omega squared, as you choose. So then you end up with 0.25 times 5.73 squared which gives us 12 or 12.3. Now I'm thinking of a 2 sig fig, so my answer should be the 2 sig figs. I've taken my omega to 3 here, so that when I get my answer to 2 here, it's still going to be accurate. So my tension is 12 newtons. Then part B, it says the string will break when the tension exceeds 60 newtons. Calculate the number of revolutions that the ball makes in 1 second when the tension is 60 newtons. So we know here that the tension is the centripetal force, and the maximum that we can have is 60 newtons. So now we're going to say that the maximum omega, if we rearrange this equation to make omega the subject, you're going to have the square root of F over mr. That's going to be our maximum omega. Down to our maximum tension. If we fill in our numbers then, we get the square root of 60 over 0.25 times 1.5, which gives us 12.6 radians per second. And that's not what we're after. We're looking for the number of revolutions the ball makes in 1 second. We're looking for the frequency. Didn't mean to do that. So we have 12.6 radians per second. So the frequency then is omega over 2 pi, our maximum frequency. And that would be 2.0 revolutions per second. Again, to 2 sig figs. So final part of the question then, part C, discuss the motion of the ball in terms of the forces that act on it. Your answer should explain why Newton's 3 laws of motion apply, and explain why in practice the string will not be horizontal. So thinking about this, I would say I'm going to take Newton's first, second and third laws one by one. So Newton's first law says that the ball will remain at rest or in a state of constant motion unless acted on by a resultant force. So I would say that although the speed is constant, the velocity is changing because the direction is changing and velocity is a vector. You're pretty much always going to say something like that in a circular motion question. So there we have Newton's first law. Newton's first law has been considered. Okay, his second law. We have the resultant force. Oops. I don't know why I struggle to write acceleration, but I always seem to. So this Newton's second law, rate of change of momentum proportional to the resultant force. This is producing an acceleration towards the the circle. This is our centripetal force. There we go, did it correctly for the first time. So there's our second law. Newton's third law. Well, here we have the action of the string on the ball is equal and opposite to the reaction of the ball on the string. So essentially the ball experiences a pull inwards and the string, the person holding the string, experiences a pull outwards. These two forces are the same type and they are in opposite directions and they are the same size. So there it is, Newton's third law. So we have discussed here how the three laws apply. The final part of the question is explain why in practice the string will not be horizontal. Well, the one force we haven't considered acting on the ball is the weight. Now, since there is no acceleration in the vertical direction, there must be a force balancing the weight so that there is no resultant force vertically. Now, the only way that can be is if there is a component of the tension. And so if the string is, or the tension is going to have a vertical component, the string cannot be, the ball cannot be horizontal. It wouldn't work. So there it is. Hopefully that helps.